All right, you may start now.
Okay. The title of the paper is Deterministic Approximation for Submodular Maximization over a Matroid in Nearly Linear Time. And yes, this is a paper on URIs with some kind of TCS stuff. I thought that was kind of interesting, so I selected this paper. And yes, so I'll like also, or maybe I think everyone knows some kind of this stuff, so I'll just review it shortly. So this is the definition of uh, submodular function, and um, also like this, we can define some monotone stuff for function with a function having a power set as a domain. Also, for sake of convenience, we define some marginal gain as like this. And yes, we can also define this for single element set, and also set with some independent structure with these three properties are called a matroid, and maximally independent set is called a base. And this is some kind of property of submodular function, and it can be proven just by some computation, but the proof in this paper is actually using a lot of computation, so this property will be used later. And this, like as I know, there was some kind of similar paper presented in season 1 of Project TCS, but difference between this paper and previous paper is the monotonicity of function. So in this paper deal with non-negative submodular function that can be probably non-monotone either, and the other three are like typical notations. Yes, and R stands for rank. So the problem that this paper wants to solve.
I have a question.
Yeah.
So by being non-monotony means that you may add you add an element and the value of the function could be decreased, right?
Yes.
Yeah. Okay. Yes.
Yes. So the problem that this paper want to solve is given a submodular function, which non-negative submodular function, which can also be on non-monotone and a matroid. We want to compute maximum value of the function among independent sets. So, like for this problem, the four in the top are result of previous work, and 2 in the bottom are result of this paper. And this paper achieved 1/4 approximation ratio with the deterministic algorithm, and also faster than previous algorithm. And so first, we will look about we'll see on algorithm with order NR complexity and approximation ratio 1/4. So this algorithm basically maintains two solution sets, S1 and S2, and it iteratively considers all elements of in the set n minus S1 minus S2, and it tries to add them in S1 or S2. And as you see in this algorithm, among them, this algorithm picked the one with maximal marginal gain. And add it, yes, to is one of them. So this algorithm is like its logic is quite simple, but we will prove that this algorithm guarantees approximation ratio 1/4. Yes, and the complexity is quite trivially order NR with assuming existence of independence oracle. Yes, so actually there's so many notations appear in the proof, so I'll just capture the image from the paper, but I'll explain the meaning of every step. So first, free E comma S1 is the set of elements of S1 added before E. And similarly, we define pre E comma S2, and also each element in O1 plus is element element that belong to both optimal solution and solution 1, and it can be added to S2, and O1 minus is defined similarly, but they cannot be added to S2. Similarly, we define O2 plus and O2 minus, and O3 is elements of optimal solution outside of S1 and S2, but cannot be added to S1. And O4 is similar as O3, so it is like the set of elements out of S1 and S2, but cannot be added to S2. So yes, I will maybe it will be better to summarize them in the board. So yes, so and also we define marginal gain of element of S1 union S2 and delta E. That means how much fs1 plus fs2 increased when E was added. Yes. So so first we will prove some lemma. This lemma one is like there's some injective function pi1 such that like these two property holds, and also there's some injective function pi2 exists defined similarly. So this lemma is intuitively the property one means at the exact moment when pi1 E is added to S1, E can also be added to S1, and this condition allow us to compare marginal gain of E and pi1 E with respect to S1. So yes, and second condition is just as written here. Yes, so yes, the whole giving whole proof to this lemma is kind long, so we will just see how to construct pi1, and yes, the proof of construction will be skipped in the lecture, and yes. So like sorry. So we can write yes, and actually, since pi1 and pi2 is defined very similarly, so we will just prove it for pi1. And so first we will write a solution set S1 as U1, U2 to US, where by the order of the added to this set, and we'll define this set LS, and we will run like run this algorithm. So the algorithm is like for J from S to 1, in decreasing order, first we define a set AJ that is sorry, I think there may be some typo. So no, there's not this was not a typo. So we first have LS, and this from LS we like inductively define LS minus 1, LS minus 2 like this, and first element of LJ that is not U1, U2 to UJ minus 1 with that if we add that to U1, U2 and UJ minus 1, it is still independent. That is definition of AJ. And yes, if like yes, and just this algorithm, running this algorithm will give construction of pi1 to us, and like and but its proof is like so I thought this proof is not this proof was like a little bit long and dirty, so I skipped this proof in the slide. So until now, we have pi1, and we can assume we have pi1 and pi2, and we can visualize them as in this figure. So element of O1 plus and O1 minus is mapped to itself by pi1, and yes, element of O2 minus and O3 are mapped to somewhere in here by pi1, and like pi2 is like similar, and yes, and so we have some more lemma to prove the algorithm. So lemma 2 is like this. So this is like actually 3 independent statements. So marginal gain of O1 plus with respect to S2 is less or equal to like this thing, and yes, but yes, so while I was making the slide, I tried to follow the author's like numbering for lemma and theorem. So I decomposed it into I also decomposed it to three lemma. So we will see the proof of first lemma. So yes, to prove this lemma, we will actually, since left one and right one are for 3 lemma or like some kind of like similar thing, so we will just prove left statement in the left for each lemma, and to prove first we prove lemma 4. So we'll consider the exact moment when E was added to S1. At the same time, I think at the same time, so we can also add E to S2. S2 because we know yes, we can, because pi1 E is E, so we can add E to S2. So since the algorithm of choice addition greedily, we know this holds. So using submodularity and simple computation, we can get this result, like adding this line for each element of O1 plus, and yes, and actually like the other 2 lemma is kind of computation too, but we'll see them. So for lemma 5, yeah. We'll consider the exact moment when pi2E is added to S2, where E is an element of O1 minus, and in this moment we can add E to S2, and E is not added to S1 yet. So yes, so yes, at this we use greedy choice too. So from greedy choice of algorithm, we have this kind of inequality, and yes, and we know that this word, so we also get this thing. So, yes, and also we sorry. We use some computation to finish the proof, and yes, and while proving lemma 6, we consider the moment when pi1 is added to S1, where E is the element of 3. Then, yes, for this we prove this thing. So at that time, we can add E to S1. So we again use greedy choice property. So we get this, because yes, and so also we again use computation to finish the proof. And yes, and so we go through one of the main theorem. So it is when it is the algorithm returns a solution with at least 1/4 approximation ratio. And yes, we for proving this, we need to use lemma presented before with like many computation. So first statement is, it is not actually that important to proving this main theorem, but it is kind of some property of this algorithm. So if like one of the two solution set is empty set, then the solution we get is optimal solution. Yes. And to prove this, we can assume one of them. So S2 is empty, and then so from greedy choice, we get this relation, because yes, and also F0 minus S1, a marginal gain of O minus S1 when with respect to empty set is yes, this inequality is we get this inequality too, because like although yes, because we know the algorithm selected that adding something, not adding something instead of adding to S2, so we get this thing too. And some yes, and proving this fact ends with some submodular inequality and computation. Yes, and and we will prove so now another some fact, and we define like S1 union S2 union O3 deleted from O as O5, and similarly define O6 for O4. Then F, so FO union S1 minus FS1 is less or equal to them. Yes. And this is because some fact that I presented at the very first part of this lecture, that some computation thing. Yes. Yes, and also this kind of inequality holds, and it can be also proven by some computation. Yes. Actually, like, I'm very sorry for these lectures proof having so many computation. And yes, yes. Also, like, these things hold, and one more, like, inequality. Yes. Yes. So actually, getting this many inequality and putting them gives proof to this theorem. Actually, yes, this proof is also I think not very interesting proof, but yes, I'll proceed shortly. This putting them together is just simple computation, because FO is from this. We have this, and we use this and this with moving S1 to and S2 to right hand side and applying this, then we get like 2FS1 plus 2FS2, and actually FS1 plus FS2 is less or equal to 2 times the maximum of them. So finally we get this thing. Yes, and although there's another like kind of fact, some fun fact for this theorem, that when the f is monotone, non-negative, and submodular function, the algorithm guarantees 1/2 approximation ratio. And yes, and second part is twin greedy fast algorithm. This algorithm also maintains two solution set as previous one, but it like use some kind of threshold to control like some optimality of adding some elements to solution set. Yes. Given some threshold, it check like every of unselected element in some order, and yes, it choose one of two solution set, and adding them like not adding them with marginal gain maximized, but if marginal if marginal gain is like less than some kind of threshold, it does not add element to solution set. Yes. So this algorithm has this algorithm is also very similar property to previous algorithm, but proving like the lemmas for this algorithm or also use computation, but I think this use the more computation. So I skipped. I didn't like put the proof of it in the slide. So actually this thing is some kind of similar thing that we see in the some of the previous slide. The only difference is 1 plus epsilon kind of term. And yes, and the authors use this property to prove the main theorem, and it is like kind of this algorithm has like a faster running time with approximation ratio 1/4 minus epsilon. Yeah. So I thought like actually the proving the algorithm are like kind of very time consuming, so and computation. So but yes, but I thought like the modeling of problems in the real world that this algorithm can be used is like kind of interesting. So we will see some extensions of these algorithms, and then we will see like some real world problem modeling. So like in Matroid, we have these two property, the two property and third property as exchange property, but if we replace the property with every two base have the size of every two base differs no more than like p times. Yes, if we use this property, then we can some kind of independent system with this property is called a p-set system. Yes. So and yes, and
can you give me some time for the p-set system? I'm now parsing it, so yeah.
Yeah, like in Matroid, we have every two base have same size, but if we replace the like exchange argument of Matroid to every two base have size difference no more than like p times, then like such like independent system is called a p-set system.
So I don't get it. I mean, so the thing is the size of the maximum base and the minimum base are under the factor p, right? So I mean,
yes.
I mean the maximum size of base is at most p times the minimum base.
Yes.
I see.
Is there any intuitive example of p set with constant p?
Like I actually I can't like give some example now because I like yes, but yes, and I don't think of some intuitive examples. Sorry for that. And maybe after the lecture, maybe I can look for some intuitive example for this and maybe share it. Yes. So, but yes, the thing is that the like in case of Matroid, it has value of p as 1, And in PSET system, if we run second algorithm in the PSET system, we can get this approximation ratio with same time complexity. And yes, the authors mentioned this result, and there's also proof, but I also skip the proofs because like PSET system is I thought PSET system was not that very like PSET system, sorry. I thought PSET system was like not very interesting, some kind of system. So I that's why I skipped the proof of this theorem. And there's some kind of applications of applications of the algorithm of the paper. So first one is like social network monitoring problem. It is like so there's like a weighted graph, like modeling the social network with vertex as like user and edge as like the weight of edge the weight of edge connecting U and V is defined as like maximum amount of content that can be go from U to V. And we consider like some partition of the set of users with according to those like some users property that is like this partition of the vertex set. And we may Ainta gave some example. Thank you. And like so we want to maximize the total amount of monitor content, but we need to keep intersection of each partition set with solution set as less or equal to some fixed size, because we want to like preserve some diversity of some kind of fairness while monitoring the network. Yes, so this is one kind of the modeling for the one kind of real world modeling of this problem. And yes, this problem can be solved using the paper's algorithm. And second one is like some kind of marketing stuff that is like the B is the budget of the company, and K like company wants to select at most like K seed nodes to promote M products, and and one node can be selected as a seed for at most one product, and like CU represents like some cost for like selecting node U as seed, and the goal of this and Fi represents some like monotone, maybe monotone or non-monotone, and some submodular function that like represents the spread of influence, and like then we want to like maximize this value. This function is like considering like both influence and budget, influence and spending. So and like there's like some kind of like there's some kind of like we can use some computation to prove like this the function that we want to maximize is actually a submodular function, and then like we can apply the algorithm of the paper to this problem. And yes,
I have a
and
question.
yes,
Are they from the paper? Like those applications are actually from excerpt from the paper?
yeah, the paper presented these two problems, and these two problems, some previous paper that some previous paper than this paper also like deal with like these. So there's another paper like deals with these two problem. So I thought like these two problem was these two problem is some real world problem.
Yeah, but it's also kind of funny because they doesn't immediately seem to me as a machine learning problem. Yeah, but so they can maybe dealt efficiently with machine learning. I don't know about that, but at the first glance they don't seem like that. So it's kind of funny.
Yes, and so like so to in conclusion, like these we saw the two algorithms from the paper. The first one is like 1/4 like approximation ratio, and second one is 1/4 minus epsilon approximation ratio. And also we see like two extensions of the algorithm where first one is like monotone constraints give first one better performance, and second one can be used in PSET system. And also we see two real world problem that the paper's algorithms can be used. And actually like when while I was preparing the presentation, yes, I thought computation is like not hard to follow in short time. So I like added I put like every proof for the first algorithm, but yes, I'm sorry for that because like I was actually like presenting this. I thought like that computation is not that much maybe not that much interesting, and also like little bit like time consuming to follow it in the lecture. Maybe I'll try to uh, I'll try to prepare a better lecture for the next time.
Thank you.
And thank you for listening. Yeah.
Is it guaranteed the same approximation ratio to last two applications?
Last two application is actually the like it is one kind of example for the for modeling of the problem that fits in this algorithm. But yes, actually I don't know it is same or better in some special case.
So the two example he listed is just an example of submodular maximization because just the cost function is just submodular. That is the only thing we have to prove, and since it's submodular, so we can just do it. Yeah.
Okay.
Yeah, but I mean, so bipartite matching is true set as Ainta said, right? I'm confused, but I think it's two sets. Because
isn't it matching set?
I guess the general matching is
is
two set as well.
Because the vertices in matching could be one of two could be covered by unmaximized.
I see. So this indeed gives a 6 to the 1 algorithm for general matching, I think, in linear time. Is it linear time?
But
Subquadratic time.
but like
Yeah, I think it is. The oracle is.
yeah, Oracle is constant. No.
I think it is because it's just about counting degrees, so we can insert and delete.
Yeah.
So probably it just gives like 6/1 minus epsilon approximation for general matching. That's funny, and that's nice actually. I think if I'm. Okay, I see. I'm sorry. I'm very sad. No. Is it? Can we put weights? No, we can't. We can't put weight. Can we put weights? So approximation doesn't work. So I mean 2/1 doesn't work if it is weights. But 6/1
Wow.
does work for weights. That's another story. But I think it doesn't. So I think you're right. But I'm confused.